thank you. And thank you all for being here. Obviously, since you're here, you feel somewhat the same way I do, that there is a better way than the standard way that probably you were taught, and that you're here to learn something about how to do that. Let's see. I'm going to back this thing up for a minute because I want to show you something, tell you a little story. This formula here, that is not a statistic, is actually what first got me thinking about doing what I do now with statistical literacy and that sort of thing, and thinking of different ways to teach statistics. When I was getting my master's degree in statistics, my mother, who's one of the smartest people I know, was getting her master's degree in social work. And she had to take statistics. She was getting her degree at Rutgers. And she wanted to prepare a little bit in advance, and so she bought one of these Statistics Made Simple books and asked me if I would help her do a little bit of advanced preparation. So we sat down at the kitchen table, and we opened the book, and the first thing there was this formula. So my mother said, okay, what's this? I said, well, this indicates the mean. She says, okay, well what is this? And I said, well, this thing here means you add up the numbers. She says, what numbers? I don't see any numbers here. And I said, well, this, and it had a little eye on it. I said, this represents the numbers. She got this puzzle book and she said, why don't they just say, add up the numbers? So I decided there had to be a better way to do this. I would say that over the years that I've been teaching statistics, which now is more than 20, things have changed to our benefit because of the technology. So that a lot of what we used to do in the classroom, we no longer need to spend time doing, because we used to teach people in ways where they were going to have to go off and actually calculate these things. You know, and that was time consuming, and they had to know how to do it. That's not the case anymore. As you know, the calculator or the computer will take care of those calculations. And so it's no longer necessary to spend half a lecture teaching students the formula, the calculation formula, or whatever it's called, for the standard deviation, for instance. It's much more important to get them to understand what a standard deviation is, because the computer will do that calculation. So I think that what's important now is to engage students in actually thinking about what they're doing, thinking about what statistics can do. Another major change, actually, that I think has happened probably before I even got involved in teaching statistics, is that these courses, the elementary statistics courses, were developed in a day and age when the only people that had to take them were people that were actually going to go on and do statistics themselves. Now, as you probably know, the majority of your students will probably never actually have to go off and do statistics. They simply have to be able to understand what other people have done. And so I think we need to put our focus on getting students to think about what they're doing, rather than actually being able to crunch formulas. So I've come up with what I call five basic principles for teaching elementary statistics. And here they are. 1, students learn best by doing one of these things, or all of these things actually, figuring things out by themselves. Now with statistics, they need guidance to do that. But if you actually get them to think about things and figure them out first, even if they don't quite get it right, I think it helps the learning process. They also learn well by explaining things to someone else. And I'm sure that all of you know this. When did you really, really learn what it was all about? When you had to teach it, right? And 3, getting involved in activities that require thought gets people to understand the material. You just let them sit there and be passive, they don't get it quite as much. You know that there's that old expression about, tell me and I'll hear you, show me and I'll see, but involve me and I'll understand. Second principle is it's important to use real and interesting examples. There was actually some research done at Stanford a few years ago, I remember reading about somewhere, that showed that people actually remember things better when feeling is involved. So if you can actually motivate things with examples that they care about, that's even better. Now obviously not all examples, the same examples aren't going to appeal to all students, but it's important to try to find ones that appeal to a majority of students. Also, I don't know about where you teach, but where I teach, we're getting more and more people from other cultures. And you start talking about baseball or things, other kind. mean baseball in the sense that male versus female, but people from other countries don't understand some of the examples that we traditionally use. Some people don't even know what a deck of cards look like. So be culturally sensitive to that. Third is something that I learned when I took media training, which my university insisted I do when I started being on television. They didn't want me going out there without them having trained me. One of the first things they teach in media training is that anything you want to say can be boiled down to 3 crucial points, 3 or fewer crucial points. You'll see politicians do this all the time. No matter what they're asked, they come back to one of those 3 points, even if it doesn't fit the question. Well, they're taught to do that. But in teaching statistics, it's also the case. And by the way, I'm going to go through each of these and show you what I mean with further examples. But by choosing fewer crucial points per topic, it will help you focus on what's important, and it will help the students focus on what's important. They won't see this huge spectrum and not know what's important and what's not. And I'll actually have you do this for the concept of confidence intervals. We'll just, so you might think about that. What are the 3 most important points when you're teaching confidence intervals? Okay, fourth. And this is actually sort of related to number 3, but it's slightly different. Don't overdo the details. Computers can handle them. Students these days don't need all the details. For example, if you're teaching regression, it's much more important to get across the idea of linearity and outliers and that sort of thing than it is to get them to completely understand what least squares means, what that term means. And I've seen this especially with new instructors. There's a temptation to teach them everything you know. Don't do it. And then finally, and this is the lesson that I learned from trying to teach my mother, different students learn differently. And so you need to show a variety of ways for any topic that you're teaching. Use words, symbols, drawings. For example, you can say add up the heights and divide by the number of players if you're finding the average height of a team, or when I get to this as an example, I'll show you other ways you can do this. So those are my 5 basic principles. And I'm going to start by going back to number 1, that students learn best by doing things. And I'm going to continue that theme when I talk about AP statistics in my workshop this afternoon and tomorrow morning that you'll be attending in smaller groups. Because one of the things that we've done in advanced placement statistics is to try to encourage, especially at the high school level, try to encourage people who teach that course to get the students involved. Of course, they have the luxury of having a full year to teach what at Davis we teach in a quarter, and where you are, you probably teach in either a quarter or a semester. So, like I said, I'll do more activities in the workshop. But for now, we go through this. The simplest kind of activity is what I call a thought question. And in my book, I start every chapter with a number of these thought questions. And so we're just going to do a few of them here, because I want to show you different ways that you can actually handle them in class, depending on the size of your class. So we're actually going to do this now. And here's the first thought question. In an experiment, researchers assign treatments to participants, whereas in an observational study, they simply observe what the participants do naturally. Give an example of a situation where an experiment would not be feasible for ethical reasons. Now, what I want you to do is pick a partner, and you don't need to flip a coin, you can just decide where you can flip a coin. And then I want one of you to explain your answer to this question to the other one. Then what I'm going to do, I have my cards and dice here, I am going to randomly pick someone in the class, and you're going to explain to the class what your partner just explained to you. So this brings in 2 of these activities. It involves you in that you each have to think about the question, okay? In fact, you can explain an answer to each other if you like, because the person I'm going to call on is going to have to explain to the class. And you have to understand what your partner said so that you can explain it back to the class, if you happen to be the lucky person selected to do that. So I want you to take a few minutes, pick a partner. If it's more convenient the way you're seated to work with 3 people together, that's okay. And I want you to answer this question, and then I'm going to pick on somebody and have that person explain not their answer, but what their partner's answer was to this question. discussing this problem, and they said they had answered the question, now they were discussing whether their students would know what a treatment was. So let me just tell you that by the time we get to this question, they've already heard this idea, the idea of a treatment at least, so they would know at this point. Okay, so what I'm going to do now is I brought dice and cards, and then depending on the setup of the room, would decide how to randomize. I'm going to roll the die to pick a row. Oh, we get row 2. That's this row. Okay, now I'm going to randomly pick a card. Have a card. 10. Okay, so we get the 10th person in the row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, yes, so you get to explain to the group what your partner said.
Well, and my partner said that it would be unethical to collect data in a class which involve personal information, such as trying to correlate height and weight, or trying to correlate grade points with certain other data. You're collecting personal information of the student. Might be offended by that.
Okay. What do people think of the answer? Any comments? Okay. What?
The treatment was not applied.
Okay. And now we may be getting into the issue of knowing what a treatment is at this point in the class, because we just started. Okay, explain. She says that doesn't involve a treatment. You explain what your partner said.
My partner said that.
Oh dear.
It would be unethical to give smoking, to expose young kids or a group of kids at an early age to a smoke environment for a period of time to determine whether or not smoking really causes lung cancer, and to keep a control group without any smoking for the baby.
Good. Right. Smoking. It's not ethical to assign people to smoke or not. Good. Now, if this were my class, and I were planning to spend more time than I am on this topic, I would take your answer as well, and I would go into the whole issue of informed consent and the ethics of doing informed consent and getting people to agree to give information or to participate in a treatment that is experimental and possibly risky and so on. So anyway, that's how I would then take this further. Okay, great, thank you. By the way, you just tied right into the example I'm going to use. I didn't pay him to do that. Okay, the next one, and actually I have a technique down here that I'm going to save for the fourth one. We're going to go to a different technique for this one because I decided it was easier. What I want you to do is take out the paper that's in or get out a piece of paper and a pen, and I want you to write down an answer to this question without talking to anybody else. Here's the question, and this gets into probability and expected values. If you were faced with the following alternatives, which would you choose? A gift of $240 guaranteed, or a 25% chance to win $1,000 and a 75% chance of getting nothing? So don't discuss with a partner. Just write down your answer, and then we're going to discuss. Now, if this were, yes, go ahead.
I'll take the 240 and run.
What? Okay, why would you do that?
Well, because the other one is you get an extended value of two treatment to the extended value, I might get to zero.
Right.
So for $10 difference, I'd rather get it 240 than I don't.
Good. So you would rather not take the risk. You would rather take the sure thing.
Yeah.
Yes. Okay. Good. And this, at this point, you can tie this into the idea, for instance, of buying lottery tickets. If you buy a lottery ticket, you're making a choice E. Well, you don't even have that good a chance. In fact, you're getting a lower expected value, but you can bring in the idea that, if you keep your money, you're guaranteed to have it. If you gamble your money, then you're taking a chance on winning a big amount, but you're making that trade-off. And of course, when you discuss this with students, you can, again, if I were going to go into this for a longer period of time, you get across the idea, and then you get across the idea of if I change these amounts, they might change their answer. If I said $24,000 versus, and so on. So there are lots of other things that we can discuss here that go beyond just the concept of expected value. They go into how we use expected value in daily life. Another version of the question, by the way, is to change it to a loss instead of a gift. And that equates to the idea of buying insurance. People are willing to put out a fixed amount of money, to lose a fixed amount of money so that they don't risk losing their house or their car. Anybody else want to comment on this one before I go? Okay, next one. Again, what I'm trying to show you here are different techniques for getting people to respond. So for this one, I'm just going to ask you to ask for a volunteer. All right, here's, and again, this is later in the book, so we have already discussed a lot of the concepts that are in this question. Suppose the weight of all women in a large university, whoops, I should say the mean weight. Yeah. Sorry, the mean weight of all women in a large university is 135 pounds with a standard deviation of 10 pounds. Let me just stick that in here. If you were to randomly sample 10 women at the university, how close do you think their average weight would be to 135 pounds? How about if you sampled 1,000 women? Would you expect the average to be closer to 135 pounds than it would be for the sample of 10 women? So this is when we first get into this idea of the sampling distribution of the mean. So, open discussion. Who wants to venture a response to this one?
Where are you sampling?
At the university. Random sample at the university. Answer the last part. Would you expect the average to be closer to 135 pounds for the sample of 1,000 or for the sample of 10? 1,000. Okay. So then I would take that and I would start. Now my students, when I first started teaching this way, I had these thought questions and they had them in advance and they were supposed to come in prepared to discuss them. Well, these were generally first and second year students. They were taking the course as a general education requirement. And what I discovered was that one day there were 2 students absent, and I realized that those 2 students had been answering most of the questions because suddenly nobody was willing to answer the questions. So I thought about how to get the students to participate a little bit more, and I discussed it with the students, and this they were interested in discussing because I gave them some choices. I could give them a quiz at the beginning of every class to answer the question, and so on. I discussed different methods. And what we came up with was this randomization technique that I used to get one of you to answer the first question. So every day I would go in, I would have a randomization technique and pick on a student who had to answer the thought question for each thought question for that day. And it really did increase their participation. They came much more prepared to answer these questions. So that's why it says possibly with random choice of respondent. Okay, this fourth one, I don't want you to write your answer, then discuss them. Now we're going to go back to the method that I switched on you, and this is to discuss it with a partner, and then we'll have a class discussion. So here's the question. Which do you think is more informative when you're given the results of a study? Confidence interval or a p-value? So I want you to discuss that with your partner or your group of 3 again, and I'll give you about 2 minutes or 3 minutes to do it, and then again, then we'll open it up to class discussion. hopefully that's what you were still discussing and you remember what you said. Who would like to venture an explanation of their answer or an answer to this question? Or an opinion, I should say, because this is an opinion question.
Right now, I feel confidence interval in a few years, p-value will be very easy because we know everything is a little calculated to find our credit card.
Okay? Which do you think is more informative? Okay?
I think it depends on the situation. If you want an estimate of the number of credit hours due to your college case, you really want a confidence interval. If you want to compare whether, say, the electronic students take significantly more courses, more credits than a human services student, then you want to be there. So there is, I don't think there is a right answer to the question.
Right, it's an opinion question. Okay? Who else would like to call for this?
I think a confidence interval, but I think I'm about 10% being wrong.
Why do you think a confidence interval? We'll judge whether you're right or wrong.
Just more informative.
Okay. Could a confidence interval tell you whether or not you can reject an hypothesis? Right, right. So it has extra information in addition. I would say confidence interval, but I could see arguments in some situations where p-value could be justified as well. But again, the point of this question is that this is an opinion question, and when I ask students this kind of question, what I'm really interested in is the justification of their response. Okay, so those are the thought questions. You're not on the spot for any more of these. Let me move on to principle number 2. And this was use good examples and get students to see their relevance. Now, again, what determines a good example is, I think, based on your audience. And in this case, happened to choose the one you chose earlier, which is Risks for Women, Passive Smoke and Obesity was the title of the article. And I'm particularly going to look at the passive smoke part. This was an article in Science News about a year ago. And let me ask you a question. This gets into the whole question of what is the risk? Why do we worry about passive smoke? So let me ask you this. Do you know anyone who's died of lung cancer?
You understand?
And then the question is, did they smoke? Were they a smoker or not? Yes, most of you are saying yes. Okay. Now, do you know anyone who's had a heart attack? Yes? Did they smoke? Some did, some didn't, okay? Here's a question. How many people do you think die from passive smoke, die from lung cancer due to passive smoke per year? What do you think an estimate would be in the United States? Right? I'll tell you but I got you to think about it, okay? The answer is, according to the Surgeon General, about 3,000. All right, now, this is what this article in Science News, which I don't need to read you because I'm going to give you the details, said. And that is, how many people a year in the United States do you think die from heart attacks that can be, according to the study, attributed to passive smoke? You think more or less than the 3,000? According to this study, many more. Many more. 30,000. So if you live with a smoker, okay, now, how did they reach this conclusion? Let's go into the example. Let's see if we believe it. All right, they looked at 32,000 nurses. This was a large nurses study that's being done. 32,000 nurses in 1982. They were aged 36 to 61 at the time. They never smoked and had no heart disease. 80% of them shared a home with a smoker. And I'll show you the data here in the next transparency. 10 years later, they looked at whether or not they had had a heart attack and whether or not they lived with a passive smoker, and that's the data. Okay, now let me just show you some statistics based on this. I'll just go down here. The proportion of heart attacks of those living with passive smokers, the proportion who had heart attacks was 0.0052. The proportion who had heart attacks who were not living with passive smokers was 0.0027. And if you look at the so-called relative risk, just compare those two numbers, it's going to be 1.93. So there's almost double the risk based on this study of having a heart attack if you live with a passive smoker, if you live with a smoker but don't smoke yourself, than if you don't live with a smoker and don't smoke yourself. So if you look at the numbers, it goes from essentially 20, let's talk about this in raw numbers, 27 per 10,000 versus 52 per 10,000, or an increase of about 25 people who would have heart attacks if they, based on living with a smoker versus not living with a smoker. Now, at this point, I would go into a discussion of other explanations, and I don't want to go into too much here because of time, but let me just ask you, do you think that if somebody lives with a smoker versus if they don't live with a smoker, is that the only lifestyle difference? Right. Right. There are likely to be other lifestyle differences, and in fact, this is an observational study. So it's really not appropriate to make a cause and effect conclusion.
If all you're getting here is numbers on the order of 2 to 1, how come we got 10 to 1 on the other side?
Oh, that was lung cancer versus heart attacks. That was dying of lung cancer versus dying of heart attack. Okay. Now let me move on to principle number 3, which was choose the 3 most important messages about a topic and then build a class around them. So I want you to think about this issue. If you were teaching the idea of a 95% confidence interval, I have my 3 down here, and we may come up with the different 3. You each will have your own 3. But what do you think are the 3 most important messages to get across when you're talking about the topic of a confidence interval? And I chose 95%, but just the idea of a confidence interval. And I chose 95% so I could write one of the messages and use that number. Anybody want to offer a suggestion for what's one of the most important points when you're teaching the concept of a confidence interval?
That you're estimating the population value and not the sample.
Okay? That you're estimating the population value and not a sample value. Okay? That's good. That wasn't one of my 3, but it should be put on there. Actually, one of my 3 sort of incorporates that. What else?
I'm not sure if I'm saying
Okay.
that you're estimating the mean rather than the individual value.
Okay, so the difference between...
That's the individual.
Right, that's good. So the difference between a confidence interval and a prediction interval, essentially, that you're estimating the mean and not getting a range that covers 95% of the individuals. Good. What does the level of confidence mean? Right. Right. Yeah, the idea that you're 95% sure that the interval is correct. Right. Right. Okay, well, let me tell you my 3, and again, you can have different 3, but that's basically my first one, was that it will cover the true value 95% of the time, but we don't know when. You could be 10%, you could be wrong. That larger samples give more precise results. That's something that I try to hammer because I think that people don't understand when they read results in the media and it says that no difference was found. They don't understand that sometimes no difference was found because there wasn't a large enough sample and thus precise enough result. So I hammer that one. And then 3, the interval is only as good as the sample from which it came, so bias in the sample will give you a bias interval. So I try to tie it into that big picture. But again, you obviously could each come up with your own 3, but the point is that you need to build your message around what you consider to be the most important points on any given topic, and you can usually narrow it down to just a couple. Okay, principle 4, don't overemphasize the details. And let me give you an example here. A confidence interval for a proportion. And I'll just show you the whole thing here. I think it's overly detailed these days to go into all of the detail of explaining all of this stuff when you can use a calculator to do this stuff, and therefore little is lost since almost everybody uses 95% confidence interval. And you can show them in more detail later if you want as more advanced topic. But to bring it all in together at the beginning, when you're first introducing the idea of this kind of confidence interval, they get confused if they're trying to figure out what alpha is and what's between 90 and 95% and 99%. To me, that's a detail that can come for those that ultimately make to do a confidence interval, but a 95% confidence interval is by far the most common. So I don't confuse them with the detail of other confidence levels when I first do this topic. The idea that for p near 0.5, essentially you can use p hat plus or minus 1 over the square root of n. You don't need to go into the whole detail of p hat q hat over n. And in fact, just to convince you, what you get for the 1.96 times the square root of p hat q hat over n for various values of n and p hat are listed here. So you can see that it's fairly close to 1 over the square root of n in all of these cases. And so little is lost by just saying, look, here's the formula, but basically it will boil down to this, 1 over the square root of n. You're doing 95% confidence, and if you have a p in this sort of medium range.
I would like to use other percents just because that makes them understand what the percent is about. Just like you said, it's important they realize that large sample gives more precise results.
Right.
I think the point of using other percents is to understand what the percent is measuring.
And I agree with you that you need to get the idea that what the 95%, the role that that plays, but not actually how to look up the z for all of these different alphas. In other words, not specifically how to compute the interval for all of these different alphas, especially since, again, the calculator now will do it for them.
But understanding the concept comes better when you see some numbers than when someone says.
Well, I suppose you could tell them, you know, it becomes this much wider if you have 99%, but that is different from having them actually have to go to a z table and look up the value. And actually, when I do talk about this, somebody always says it, so it's...
Well, it's learning styles, too. Some will learn it well to say that this goes this way because of the size, and some will learn it better because I see the 3 different numbers of the z's, and that's why I understand.
Yeah, and again, I think that you can make those points, but to make them initially doesn't permit, and again, that may be one of your 3 points, so you may want to make that point. But if you try to do everything at the beginning, they don't understand what you consider to be most important and what you consider to be less important. For me, that's less important because, well, generally the students I teach are students that I just want to understand when they read about a confidence interval. And it's almost always the case that a confidence interval presented somewhere as a 95% confidence interval. Okay, and then the 5th principle is the idea that students learn differently. And let me just show you 4 different ways to explain the sample mean. There's my mother's method. Add them up and divide by 3. So suppose we're just trying to get a sample mean for 3 heights of, say, 3 siblings. Add them up and divide by 3. That's the way, I guess, social workers would do it. You can actually spell out the numbers. Just write them down. Okay. You can use the formula. There are students who learn best that way. Obviously, engineering students, for example, like to see formulas for everything. So you can present it that way for certain groups of students. And again, I would do multiple methods in every class because, again, different people. Or some people would prefer to see a little picture here. The mean is where the thing balances. If you were to take a little rectangle and fill it with water, and put it on each of these heights. Now, obviously, this doesn't tell them how to calculate it, so you can do one of the other methods along with this, but it does help some people understand.
But it is an issue, your lesson shouldn't be minimized, because a lot of students do not understand what happens when you slide them along that, teeter-totter, seesaw, whatever you want to call it.
Yeah.
You really need to do that once, at least once, to let them know and understand what happens when a huge group out here at 60 and one sitting out at 75. What happens at the same mean? What do you mean?
Yeah, that's true, yeah.
Some people are visual learners.
Right, that's right, yep. Okay, now let me just move quickly on because I only have a few minutes left. And as I said, I'm going to go into this in a lot more detail when I do the AP statistics discussion groups. But I want to go into a little more detail about what I mean by activities, because I think activities are really important in statistics classes. And one of my colleagues puts it hands-on, minds on. You get them busy, you turn on their minds as well. This particular person is a geologist, and I guess they get to do a lot more activities, more natural activities in geology. But so you get students involved in thinking. Now, activities don't have to be physical activities. Thought questions are activities, as long as you're engaging them actively. That's what I would call an activity. Activity. I don't think activities where you give them a complete menu of instructions are much use. I've seen some people talk about activities where they actually give the kids and students a whole list of what, do this step, then do this step, then do this step. Well, that's not what I would consider to be a thought-provoking activity. That's just following a set of instructions. You've got to get them involved in thinking about the activity for it to count. One thing about activities that bothers some people and makes them a little more difficult than the way maybe we're all used to lecturing is that they won't necessarily have one right way to do them. So it's the thought process that counts. You see that in the workshop where I'm going to do an activity with you. There's not going to be one right way to do it. I think activities provide an excellent tool for integrating the important aspects of statistics, the design, the data collection, the data analysis, and the interpretation. And again, the activity we'll do in the workshop will do that. We're going to design an experiment and carry it out during the workshop. And then, let me just do this. Activities can be done individually or in teams. They can be done in the classroom or outside the classroom. And finally, more and more these days, computers can be used to simulate activities, and as long as it involves getting the student to think, then that's also a worthwhile activity. For example, one of the activities that, I don't know if Alex will show it when he does his presentation, but the idea of that we have on the computer is having students have a target correlation coefficient and have them try to draw a set of points that reaches that target correlation. And the computer will, the computer tells them immediately whether or not they've gotten close or what the actual correlation is for the points that they've drawn. All right, let me just give you some quick classroom examples of activities. You can do simple data collection and summary. In my classes, sometimes I teach 200 students in one very large class, and I do this. I go through and do pulse rates, have them all take their pulse, and then we create a stem and leaf diagram. And in fact, we do one on each side, one for males and one for females, so we can compare male and female pulse rates. And it's very, very quick to go through the whole class and get them to read off what their pulse was. It just takes 2 minutes to write them all down. And it helps you illustrate shape, median, range, you can look for outliers, and so on. First time I did this, I had one student whose pulse was 120. So it was great. It worked perfectly. I could illustrate this idea of an outlier. Turned out she was on some kind of medication. She came up after class and said, that was me. You can get the whole class involved in the same activity, and actually we're going to do this one in the discussion group, in the ESP test, where you explain the experiment, construct a hypothesis or other inference method, collect the data, test the hypotheses, and then get confidence intervals if that's inappropriate. And then have a discussion about the results. Other explanations for the results, sample size issues, all of that. That works better if you have a slightly smaller class, obviously, to get them all involved in doing an experiment. You can do team projects in class, and some of you who teach where you have a lab or a discussion section associated with the class might do this, where you have each team doing an experiment, and then they come together and report their results to the class at the end. And then you compare results across teams to show the idea of variability. So when you do an experiment multiple times, it comes out different each time. And again, taste testing, where you bring in Coke and Pepsi or whatever. Okay? It's a good one for that. And then you can have them do projects outside of class, and I'll just put this up here, either as individuals or in teams, and again, bring their results to class and discuss the variability in the results. And here are just some examples you can use. Which are more popular in your area, red or white cars? Have the class design a study, or have the individuals or the teams design a study, collect the data, analyze the results, present to the class, and then have a discussion. Because they have to think about sampling issues. They have to think about how large a sample to collect. Where should they collect the sample, etc. Okay? 2, design and conduct a survey using 2 different forms of the same question, where one is clearly biased and the other is designed to be fair. And obviously use different groups of respondents, and then compare the percent that respond each way for the 2 versions. An example I have in my book and that I had a student do was where you ask people, if you found a wallet with $20 in it, would you do the honest thing and return it? Versus, if you found a wallet with $20 in it, what would you do?
Just smart thing.
You can design and conduct a study to see which of 2 grocery stores in your area have higher prices for common items. And there are lots of issues to discuss here, whether or not to count sales, use name brands versus store brands, etc., and then determine how to analyze the data. Another example where they'd actually have to do an experiment. Some research has shown that listening to Mozart makes you smarter. In fact, I had that example in my book, and then I found a CD that's actually, the name of the CD is Mozart Makes You Smarter. It's a Mozart CD. So you can just have them design and conduct a study in which you ask people to listen to Mozart and then take a quiz, maybe a quick algebra quiz, and then create an appropriate control group or a paired design, and then formulate and test hypotheses about whether or not listening to Mozart actually changed the results. And there are design issues like proper randomization, blind and double blind, all kinds of issues. Even if you don't actually have them carry it out, you can have them design an experiment like this and then discuss the issues surrounding it. So these are lots of things that you can do to get them thinking about the whole process. And just a final summary then on activities. They should be done to encourage independent thinking. They can be individual or group, but they should always include group discussion. It's always interesting for students to hear how differently they all think. The activities provide a good method for integrating statistical work. Normally when we teach in class, we teach an example, here's the data, here's how you construct a confidence interval. They don't see it in the bigger picture. They don't see the whole process. These activities get them to see the whole process. Hypothesis formulation, why do you even care? What's the question? What the question is interest. Designing an experiment around that question. Collecting data in a smart way, so you don't bias data. Summarizing the data, looking for outliers, etc. Doing a formal statistical analysis, making conclusions based on that, and then finally considering possible alternative explanations for the results, like we did for the passive smoke example. So they can go through this whole process with an activity-based project that you have them do. So, okay, well, I'm going to end there. Looks like I'm 2 minutes over, and as I said, I'll continue this theme in my workshop this afternoon and tomorrow morning.
I'd like to correct you, Jesse. You're not 2 minutes over. We got you started. It would be a crying shame if we didn't take a few moments for questions and comments from Jessica at this time. If that's okay. Are there any that folks that have? Yes.
I have a question about the pulse rates. You said the students come up after class. Do you have a way that you collect the data so they don't have to tell everyone what their pulse rate is?
Oh, that's a good question. In that case, I actually had them write them down and pass it forward, and then I had somebody quickly read off to me what they were. Other classes, I have actually had them call out their pulse rate, and I've never had anyone complain about doing that, but it is an issue I suppose I should ask the class in advance.
I have them write them down, and I have them an option that they do not need to write down.
Yeah, that's probably a
I
better,
say that,
yeah, that
not
gets
right.
back to your issue. Yeah, that you might not want to ask students. Pulse rate's the only thing I've asked them to say publicly. Other things I generally have them write down, but that's a good point to think about for your class.
I have to write down how much money they have in their pocket, which is the problem. They're carrying $500.
Yeah. May want to leave that other option.
Like 8 weeks later to compare.
Oh, that's a good idea. Excellent.
I have them read the daily paper, and look at the obituary column, because they never read it. Tell me the average age, and in theory, you say, okay, I say the average age is 75. Of course, I was trained as an actuary.
Ah,
Makes them wake up and see the paper and see how what the
Yeah.
average age is for female versus male.
Oh,
This is
that's
near the
good.
end of the first book, so now they have an idea of how to handle this, and they do it as a team project.
that's great.
Tom?
Yeah. Do you have any experience with distance learning, teaching statistics in incorporating some of these principles with some of the challenges there?
Not at this point with distance learning, no. Other than the obvious, letting my students, having a web page and letting them email, use email, that sort of thing, but no, not beyond the traditional classroom.
Yes.
What they will do is they expose your students to the concepts before they come and utilize it the way you expect them. You start with the concepts and then ask them to ponder about this, or you simply give them the first thing and then you discuss the idea of the personality.
I used to teach in a fairly traditional way, although I always incorporated some of these ideas. Then when I started teaching this general education course, statistical literacy course, it changed the way I teach all my other courses. Now I start all my courses by having them discuss concepts first, because I think that statistics is actually much more intuitive than we realize if you do it right, that they will actually come up with things that are fairly close to the right way to do things if you just ask them about the concepts first. So for instance, the idea of getting a biased sample versus a good sample, if you get them to discuss that idea, they'll actually come pretty close to the concept of a random sample. So I try to get them to think about the ideas first before I tell them how we do things in all my classes now, even the math stat class, the advanced math stat class that I teach.
Yes.
What happens when you have students who have had a high school course in statistics who then give you the formulas as answers to these questions?
Well, that's an interesting question. It doesn't come up that often, actually, but you have to retrain them. It does come up, actually, where if we can get people to teach AP statistics the way we're hoping, then they'll come out with the right method. But it does come up where you have someone who thinks they already know how to do this stuff. And it's like any other part of the discussion. That's just one aspect of how you get somebody who does something not quite the way you would like them to do it. And it depends on what they say in the situation. But generally what I would probably do in something like that is ask the class, this, obviously I would say something like, obviously this person's had statistics before. Somebody who hasn't had statistics, who doesn't already know that, can you tell me what you think? Or that kind of thing.
We're going to take a break now. I don't know about you, but some of these ideas seem to me very exciting. Others are really tough for me to get my mind around. But I'm working on it. It's been very challenging to teach this course with your book. And I'm not doing it as well as I ought to. I say that in spite of the fact that some of my students have started to come in and join us here. And so I think, but that's true. I hope that I'll be able to do it better. But this has been a marvelous time, and I hope that we'll get a chance to talk to you some more. Thank you so much.
Yeah, you're welcome.